Thanks very much. I have to say, it's really nice to have the opportunity to 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 almost see you all, or at least be able to converse through chat in real time. I mean, um, we have appreciated these dimensions of our conferences in the era that we go through quite a bit. I think all of us have. So it's a pleasure to be here, and thank you for the invitation. I'm going to talk to you about work that has evolved into this title of real-time intelligence, which is a working title, but it's stuck in our heads, in our team. What I'm going to present today is a few high-level ideas, a few lower-level ideas, and some vertically integrated ideas that are driving us from now to the future. And this is work that's done by my team here at the EPFL. So let me see.
Oh, Anastasia, just one remark for the audience. If you have questions, please type them in the chat and we'll select some questions after Natasha is done. Sorry, Natasha.
As you wish. I'm happy to also answer questions in real time, because otherwise I wouldn't live to my title, you know. So I mean, it's up to you. I don't mind doing this real live talk. So without further ado, let's talk about change. You know, people welcome change because it makes things interesting. It makes life interesting, right? But really, sometimes if you think about it, change really means trouble. And especially when for data management, we deal with nothing but change, right? Change in data, volume, and all the other V's growing exponentially, change in workloads where applications are growing both in number, but also in heterogeneity. But at the same time, in the hardware heterogeneity is a new old thing, meaning that the hardware has been changing for decades now. It's probably the fastest changing component of the a vertical computational stack that we call a data management infrastructure. But it's really all the change that's happening in the hardware has started hitting us pretty hard in the last decade, just because the hardware itself has hit a brick wall and has been throwing to the software quite a bit of responsibility to do things right. At the same time, as I said, we have the other two dimensions that have been there a bit more prominently, but also very importantly. So as ever, data management faces, and a word that's missing here is increasingly more critical challenges. I think our challenges are growing pretty much like this data curve here in this rate. Can you see my the pointer here?
Yes.
That's great. So I've come to realize in the work that my group and I have been doing in the past few years that preparation really kills discovery. I mean, thinking very simply about a person who has data, raw data here, and wants to ask some questions, what they have to do in one realization or other, and maybe some systems allow to skip some steps or not, but just to have here the worst or average case scenario, you need to build a database in some way, or a data lake in which you somehow load the data or register the data or ingest the data. And then you need to make the data usable by bringing it into the state that's considered by everybody valid, so its veracity is guaranteed. Then the database needs to be tuned, access methods need to be built, permanent ones or temporary ones, so that the data access is guaranteed fast. And then finally, only as a fourth step here, we can ask a question that turns the data into useful information. Then the system uses some sort of resource planning for the execution of the question. And then finally, we can just run the question and get an answer. And by that time, especially in situations where the data is a lot, the questions are complex, there's a lot depending on the question, people throw a lot of money and effort to this process so that they valorize the data as much as possible. So the problem with this process is really that the fact that all of this preparation cost grows not with the used data, not with the data that's useful to us, which is typically a small percentage of the owned data, but it grows with the owned data, with the amount of data that we own, because when we prepare the data, we really don't know what's going to be used with certainty. So we prepare for pretty much anything. So, and on top of it, any planning that we do is quite expensive and a lot of times it's wrong. So what we've been working on as an umbrella project in this effort is a pay-as-you-go system where the user asks a query, and there's been no preparation about the data whatsoever. Then we generate an access code, access paths, and any filtering code that we need to generate just by looking at the query and figuring out what data it's going to be using. We go, using this code, we go directly to the data, we fish out all the necessary data, and then we bring the data back and we execute the query using this generated code as if we just created a small database system for only that query and that data that this query uses. So this allows us essentially to answer the query within the leanest possible way. Now, for performance reasons, well, this gives us functionality. This gives us the ability to answer a query without having prepared the data, but of course it's really slow. So for performance reasons, we cache all useful data and information. And by cache, I mean actually a pretty elaborate infrastructure that allows us to intelligently understand, structure internally all of the data that's been useful so far and the code that's been generated that's likely to be used again. And that way we can make the system more and more efficient by learning what the user has been doing and what has been useful to them. Now, without going through too many details on this slide, I will in a minute, what we make the user happier because the user hasn't been preparing any of the data, has just asked the question and has gotten the response. And the objective here is to be able to give the user who has been waiting for the answer to the query for a long time after they've received the data, who has been waiting for the whatever IT department to prepare the data before they're ready to ask questions, a much faster insight into the data than if they had to prepare it. So, and by preparing the data essentially in real time and only when it's needed, when the data are needed. So I just want to give you a little bit of a few bits and pieces of what we mean by this magic looking data to insight time equals 0 and no preparation business. There's several stages really to preparing the data, and perhaps the costliest one is what we call data cleaning, or what I like to address as data sanitization. Essentially, this is the process by which the data, we confirm its veracity. So the data, as it comes in, may have normalization issues, may have inaccuracies, omissions, may even be subjectively dirty, meaning that one user might consider it acceptable, another user, however, might consider that it needs some cleaning or some modification in order for it to become acceptable in terms of accuracy. In any event, the classical thing to do is to take a database that's dirty and clean it, and then create a clean database and ask the query to the clean database. And because of a lot of reasons, breadth of different errors that can happen, the subjectivity of the actual action of data cleaning, even the multitude of meanings that one can give to the word veracity, we find this process as actually very monolithic and prone to inaccuracies in and of itself. So we find that it's much better to clean the data as needed and as much as needed in a process that's going to be inevitably weaved with the interactive analysis. So in a very at a very high level, what we do is that we allow the query to go into the dirty database, into the dirty version, if you will, of the data, and then we make the cleaning a part of the processing of the query. We weave essentially all of the error detection and also error correction as part of the query execution as it is, as part of the query planning, essentially. So if you will, the query plan that's generated is a plan that contains not only query execution operators, but also data cleaning operators, and these operators perform together with the data to give with the query execution of the operators to give the result. In this process, we will have some side effects that may affect performance in real time. For example, in the system here, in this example here, you've got Los Angeles and San Francisco with the same zip code. So there's clearly an error here, and the system will include the violation. We include an operator which will detect the violation of the functional dependency here, and then we'll go around trying to fix the problem in a probabilistic way. And all of this work will be weaved into the query plan. Of course, this might mean that you will fish out more data than you would otherwise, and that means that you will probably go through a bit more data than if you had already cleaned the database. But then again, you only clean the useful data with those probabilistic fixes. So in the net, you're doing useful work for the data that's actually of interest to the application. So in the same spirit of the pay-as-you-go, one can go to the other side, which is not just preparing the data, but also going to this third step, which is about automatic tuning and creating indexes and views and things like that, and do the same. Look at how the data is used. And on the left-hand side here, you just see the data depicted as attributes, as columns of attributes. And then you can see different horizontal lines here that represent relative hotness of the data. So maybe that data it's more hot and that data is a lot less, or so on and so forth. So these lines can move up and down depending on how important is the data to the past queries or not. And by essentially skipping non-important data and at the same time looking at the nature of the accesses to the important data, one can start, after a point when those lines sort of mature and don't move anymore, start building structures that can be either value existence style structures like Bloom filters or value position style structures like p-trees, and use those as indexes. And the point here is that you don't build anything from the beginning, but you start by asking questions, what would be the cost and what would be the gain if I built this index or not? And at some point you might build a B tree, and then moving on, you might build in a different part of the file, you might build a Bloom filter, and so on and so forth. So the bottom line here is that the index cannot and should not be a static structure, because again, it's very presumptuous otherwise about information that's only known much later. And that way, the maximum gain of the index is just amortized by the cost to build, which is information that we have at the time of the execution. And then in the third step, the planning step, we've looked as a community a lot into query optimization. That has been an inevitable first step in order to ask a query, and a pretty costly first part in the critical path of execution of the query. And there's been quite a few efforts for dynamic query optimization, and at the same time, there's been quite a few efforts for multi-query optimization. But what we are trying to do in the scenario of real-time intelligent systems here is to bring those two things together. So dynamic reoptimization is a great thing because one query learns from the previous one. And if we actually reduce the granularity here, make it finer, one level of the query plan can learn from the previous level of the query plan, or one execution of an operator can learn from a previous execution of an operator. And that actually can be much more efficient and interesting if it's coupled with multi-query optimization. All of a sudden, when you do dynamic query optimization or online or real-time query optimization, where actually you change the query plan as you execute the query, and at the same time, you acknowledge that there's more than one queries in the system that may be using the same tables with similar or overlapping predicates, you might find some very interesting ways to combine the two and actually do a much better job by applying techniques like reinforcement learning to help you decide how to change the query plan every step of the way. So here I'm just showing, and then basically it's the same idea as with many other re-optimization techniques or dynamic learning optimization techniques, where you have a policy, an initial policy, which is continuously reinforced and adapted by the execution and the results of the execution. And here, those three queries in the systems, they have some commonalities in their joins and the tables they access, and then they have also some differences. And then they start in one way, from a subset of table R that's processed in the current episode, and then the policies candidates are S and T, and then the policy chooses maybe S, which actually serves all three queries, and then it appends it to the global plan and then moves to the next decision. And then the policy will choose the join with T, which exists only in Q1, and then Q1 is ready. So on and so forth. So you get all these decisions to happen in real time, and the plan basically becomes this visual mess, but in reality, it's a plan that changes every step of the way, so that finally, every step of the way, you make the best possible allocation of resources and sharing of output that you could have made with the information that you have at that moment. So this is essentially some three examples. I've just shown you three examples that you can do for steps 1, which is the data preparation, the cleaning; 2, which is tuning, index, how you can make them in real time; and 3, which is the query optimization. But then we have 2 more dimensions of heterogeneity and change here, and these actually require a lot more fundamental thinking about how to vertically integrate the information that we have without losing the advantages of separation of concerns in each horizontal module of our systems. And here I'm talking about the 2 kinds of heterogeneity that we encountered most often. One is data heterogeneity, so data format heterogeneity here, and the other one is hardware heterogeneity, whereas data format heterogeneity is the one that mostly impacts how efficiently we will access and cache data in order to achieve this pay-as-you-go system. And here I have a specific example, which we worked with for a while with Symantec. This is basically the data silo of Symantec. They receive periodically JSON files, which are collected through spam traps. And these contain information about spam emails that the Symantec software has identified and processed. And then these files are the input to the data mining workflows of Symantec, and the operations that are performed on them are basically classification, clustering, and these kinds of stuff. And then the output of this workflow is appended to CSV files. And these contain information like, for example, what's the identifier of each email, various assigned classes, and so on and so forth. And finally, data is loaded in a relational database, and then you do further calculations there. Now, these data sets, what's important here, that these data sets contain information that's complementary to each other. So analyzing the span data involves queries touching every combination of the heterogeneous databases. And obviously, combining this information is really not trivial, right? The major data management challenge here lies in allowing for ad hoc queries, because we don't know the queries. We don't know anything about the queries ahead of time over diverse data formats, and do that really fast, because we're talking about active spam bot detection. So in our previous system, one could say that we've got this data to system and query to system flow here. So the system, the database system, the classical traditional database system, is the center of the universe, and everything has to adapt to it. Proteus is the name of our prototype for to do things differently, to do things intelligently in real time, where we essentially reverse these arrows here, and instead of the data adapting to the system adapts to the data. Just like you have an adapter when you go to a country, you don't expect the country to change their plugs to the one that you have for your laptop. You carry an adapter for that country. So it's very similar to that. It's like a plugin. And at the same time, using efficient code generation, we can do the same, not only to address the variability in data formats, but to address also the variability in different kinds of operations that we might need to access to the data, and code generate in real time when we know what the use of the data will be. So a classical database, so this is one of the queries that we handled in the semantic system. And then a classical database would load the data into the query and then into the system, and then it would create this or another, this is an example, query plan, and would then run the query plan on the loaded database. So Proteus doesn't build a database. Essentially, when the query comes in, it creates a query plan, and then it code generates the access paths directly, and then it code generates all of the operators that are going to be needed, and then it builds position caches and data caches and other kinds of information that's updated as the query is running to help performance for future queries. So that's, I'm going through this a bit faster because it's kind of work that we've been doing for a while here, and other people have actually been doing that also, or similar versions to this with compiling close to the machine. And this helps a lot to adapt the system and keep lean code and not have a tremendous amounts of code. And my student who is graduating this month actually has been analyzing performance of database systems workloads on heterogeneous hardware. And he's been concluding that newer systems, they are way, way, way faster, and they have to execute way fewer instructions. And the reason is that newer systems are simply optimized in similar and other ways. So real-time intelligence works in query execution and code generation. Wherever we can do it, it's actually going to be paying off. Last but not least, I'd like to talk about how the hardware virtualization is needed to tame hardware heterogeneity. And this is a subject that's very close to my heart because hardware has been tremendous in giving us one and pretty much only one capability: parallelism. And the reason why we perceive it differently with every generation of hardware that's available is because parallelism has been coming in implicit or explicit forms and in different levels of granularity. And that makes us reconsider our system architectures, just because we cannot harness it in the same way depending on the different formats that it has. As we all know, being hardware oblivious allows us to have portable code, but at the same time, our performance of the system is not as good as if we had hardware conscious code, right? At the same time, if we build code very close to the hardware, we're gonna run the danger of our code only running on the platform that we developed it in. So this is a fundamental trade-off. And when heterogeneous hardware comes in, this trade-off is all the more pronounced, because this is an additional dimension. For example, with GPUs, and everybody knows how amazingly useful they can be for query processing, we run this trade-off nevertheless in a much more pronounced way. So in response, abstraction is the solution to a lot of problems. Maybe all of the complex problems we have in computer science are tamed using the right levels of abstraction. And in this case, we found abstraction to work quite a bit. So looking at analytical queries and looking at, say, for example, the different devices we have in any given machine, we can coarsely divide the kinds of computation we need to have in inter-device. So executed, and that means essentially that we recognize that we have different devices in the system. So and so we build execution modules that encapsulate this heterogeneity, those different devices, allow for the control, for example, to go from one device to the other, for one kind of device to the other. I'll give you an example in a minute. Then we need to address portability inside one device, no matter what device that is, because when we start the query, we don't know what device each part of this query is going to be executing on. And that has to be decided later, because it's a matter of efficiency. It's not a matter of query definition. So we need to be able to specialize online depending on what device we're running in. We need to be able to have portable operators intra-device. And then at the same time, when we are running one operator, for example, Peter's cache, join operators that are optimized for the cache, for example, if I'd like to move them to GPUs, I'm going to need to do different things to handle the cache infrastructure of the GPU. So that cannot happen ahead of time, because I don't know if that operator, the join operator, will be running on GPU or on a CPU. So I'm going to need to be able to code gen there to write fast algorithms which are close to microarchitecture. So then when I code gen, I have all the necessary mappings to map to the hardware infrastructure. So we go from, if you will, the other way around. We go from finer granularity, intra-operator, so inside the operator, which part of the operator need to know a lot more about the microarchitecture and which ones are oblivious, all the way through intra-device to inter-device, where for the first time we recognize that we have different kinds. And if we address these problems differently, we can do things like, for example, what my student Pericles did in last year's head exchange paper, where he took this whole concept of exchange operators and he made them, he created a family of operators that can be used to control the flow across devices to rather express the control flow and the data flow. So if you have a pretty simple looking query here, that just a scan and a filter and aggregate, then you could say, for example, that the scan would better run on the CPU because that's where the data is. The filter could run on the GPU, and then the aggregation can run back on the CPU. You can really do that in a fine-grained way and in a transparent way by creating all of these operators in red are control and data flow operators that are introduced to be able to move the control to spawn different parallel versions of the query plan execution to move the control from one kind of device to the other, to pack or unpack the data in order to express the relationship between threads and execution in different devices, and so on and so forth. So creating new operators, we can separate the levels and encapsulate the device heterogeneity and execute on multiple different kinds of devices. And last but not least, for application heterogeneity, as we all know, the world is moving to HTAP. We've got OLTP on one side and OLAP on the other side. And there we've got interesting problems because everybody says that, oh, OLTP better run on CPUs because they're task parallel, and OLAP better run on GPUs because they're data parallel. But in reality, that's easier said than done, right? Because OLAP running on GPUs, this means that the GPU needs to fetch all of the data from main memory at the same time as the CPU, the operational part, is creating it, right? So the operational part generates the data, the analytics part consumes the data, and then that data is protected by concurrency control, and it has to go to GPU through NVLink if we're lucky, but maybe PCIe depending on the infrastructure that we're on. So really there we need just-in-time scheduling decisions which allow for the freshest possible data to come into the GPUs, and providing a combination of different techniques to protect the data for concurrency control, to avoid the overheads from the critical path, but also to ensure fresh data. And the space there is really interesting because on the one side, you've got the classical ETL, like what I showed before. So one side, you've got OLTP, the other side, you've got OLAP, and then there is the clear separation of concerns. And on the other side, you've got completely co-located OLTP and OLAP sharing resources at 100%. And you've got a spectrum where your data access is mostly fresh here because everybody can access everything in theory, but the performance isolation is much better done on this spectrum. And here you've got different levels of accesses that allow you to be able to access the data and optimize for both freshness, but also for elastic computation as needed, given the dynamic resources. And so that's just a very quick overview of what we've been doing, trying to virtualize, use just-in-time for data, for workloads, and for the hardware. And here, I'd like to finish at least the technical part by saying that we've had 5 V's for data, at least 5. I don't know, maybe there's some more, but there were variety, veracity, volume, value, and velocity. And it seems like variety is growing in breadth, and we've got actually variety not only on the data, but also in the entire operational environment. And there's unpredictability because of this heterogeneity and variety. The veracity is very important, again, not only for the data, but also if you think about it as freshness, it really goes beyond it, and it affects the decisions and the importance of these decisions. And then volume there is, in my mind, it's very connected to systems volume, right? Because we've got so many layers in our system architectures here that we need to make them talk to each other, but at the same time being separated from each other in terms of concerns in order to achieve efficient execution and portability. Then we've got value, where the value is not only about the data, but it's also about the resources. And then finally, we've got the velocity there. If you see the newer pictures of what systems look like and what the interconnects look like. I mean, they used to look like this, and now they look like this, right? So GPU boards, and so so there's a lot of the velocity at which the technology is running is really a very important part of our thinking that we really need to have real-time intelligent systems, as opposed to what we have now, which are intelligent real-time systems, or real-time intelligent systems to catch up with this very evolving landscape. So systems need to incorporate change into the design as a native design, to anticipate this change, to react, learning from the errors, because they're going to be only as efficient as their component that's least adaptive. I'd like to finish by saying that being reactive keeps you young, and being optimistic also keeps you young. And there is Martin Kirsten, who has always been reactive and has always been optimistic. So if you go and tell him something, his first reaction is to put on a smile. And then he's gonna start the wheels of this amazing imagination of his. And he's gonna say something inspiring, because he's inspired himself. Every time I make a talk, including this one, Martin's talks are my golden standard. I think I remember his visionary talks. I remember his talks about data management, the nature of data, about systems, his keynotes, and they've always started with something that made me stop what I'm thinking about and start paying attention. And I think Martin has always been a big inspiration in our community. He's always had the most down to earth, but at the same time, full of imagination advice. And to me, and I'm sure to many others, has been a role model. So thank you, Martin. I'm very happy to be here and honored, and I'll take your questions now.
Thanks, Natasha. Maybe we have time for one just-in-time question from the audience. There is one. Actually, did not see them in the chat. So do you think, Natasha, that this this reactivity and this heterogeneity stops with GPUs, or is this only the beginning of even more wilder hardware kinds? And what would you see appear most prominently?
So if we're gonna think about heterogeneous hardware, we cannot stop with GPUs, right? GPUs are just a very lending example because they're easy to program and they're accessible to most of us, so we can actually experiment with our ideas. But the concepts that we're bringing forth here go beyond the specific kind of hardware. They go beyond the GPUs themselves. They are concepts that we need to use, to be able to use for other kinds of hardware as well, in the sense that when a new kind of hardware comes in, we need to be able to define the things that can bring it together with the rest of the system, and just add the definition to the system, and the system needs to be able to take advantage of it without architectural changes. And so just like
we have some work to do still, indeed.
We do, but that's why it's so interesting, right? That's why we can do that. And if there's, I mean, this is the community, just like I view computer science as the I don't want to say common denominator, because it kind of puts us on the bottom of the fraction, but as a center really of all the sciences, right? Because we make all the sciences, we don't just accelerate them, we make them efficient. We make them feasible. Efficiency means feasibility in so many ways. So I view data management I think data management has the same role within computer science as computer science has within the sciences, among the sciences. So data management is really at the center, and we have a huge responsibility to be able to adapt to the newcomers who say, oh, you know, I need you, right? So there's so many sectors in business and science that don't use computer science, don't use data management efficiently. And this is one of the steps that we should bring forth.
With that, thanks a lot, Anastasia, for your talk.